Hello, in this video I want to show you how to solve the following problem. What if I gave you a point charge like this that's positive and I asked you what is the electric field at some location here, some distance away from that point charge? How could you figure out what the electric field would be? Well, what I'm going to do in this video is show you how to use Gauss's law to calculate that electric field for any location at any distance from this point charge. How do we do it? Well, let's go back to this. This is Gauss's law stated right here, and it basically says that the E field times the area equals the charge enclosed divided by epsilon naught. Well, what does this mean? Well, the basic idea behind Gauss's law is just to use this equation to solve for E. And I'm going to do that by taking this and dividing both sides by A so that I isolate E on the left-hand side by itself. Well, what is E perpendicular? This little sign here, and then what is A? What we're going to do is we're going to pick a surface, some kind of surface, and we're going to put it around our point charge. And we're going to do it in such a way so that when I pick that surface, each one of these field lines is going to intersect the surface at a 90-degree angle. I'll show you more about that in a minute. But let's go back and just figure out what these field lines are. Remember, a field line is the direction that a little tiny positive test charge would move in if I placed it near this charge. So this is a big positive charge here. If I took a tiny little positive charge right there, like a speck of dust, which way would it run? It would run away that way. It would run away that way if I placed it here, and if I placed it here, it would run away that way. These are the field lines, and that's why they're emanating outward, like the spokes of a bicycle wheel, from this positive charge. Now what I want to do is I want to create a surface that has a certain area. This will be called my Gaussian surface, and I want to place it in such a manner, if I pick it correctly, that I will have a 90-degree angle between all of the field lines and that surface. Now, I could pick a really weirdly shaped thing like that. Let's call that a Gaussian amoeba. But then under those conditions, I wouldn't always have a 90-degree angle. Look at some of these lines. They're not always intersecting at 90 degrees. You know, like say this one over here, it's not intersecting at 90 degrees, that one that was there. So what I want is something that always intersects at 90 degrees. How can I do that? Well, if I pick a sphere, a Gaussian sphere that goes around this point charge with all of its field lines emanating outward. Now remember, this is a three-dimensional object. I'm drawing it as two-dimensional right here, but you can imagine it being kind of like a sea urchin. It's a little tiny ball, maybe like a ping pong ball, and it's got all these spines emanating from it in all directions in 3 dimensions. So it's more like a spherical sea urchin. Okay? What I want to do is put a surface around that sea urchin such that every one of the spikes intersects that surface at a 90-degree angle. That can happen if I pick a sphere that goes around like this. And as you can see, right around here, that's 90 degrees. Here it's 90 degrees. Here it'll be 90 degrees. Here it'll be 90 degrees. And that gives me what's called E perpendicular. All the electric field lines are intersecting the area of this surface that I picked in a perpendicular fashion. If I do that, then I don't have to worry about calculating cosines and all that other stuff. And so this makes the math easy. So then I can just say E times the surface area of a sphere. That's the area right there, 4 pi r squared. This is E perpendicular, it just becomes E. And now I make that equal to Q enclosed. That's the charge inside my Gaussian sphere. So my Gaussian sphere encircles this charge Q right here. Back there, this little guy. So as a result of that, there's my charge. As a result of that, I can say Q enclosed is there. I divide it by this constant epsilon naught. There's the area of the Gaussian surface that I put around it, a sphere. And now I've got this. Now I want to solve for E. So let's do that in the next slide. In the next slide, we do this. Okay, so we started with this equation on the last slide, right, like that. I divide both sides by 4 pi r squared. So I get E equals 1 over 4 pi r squared, like that. And now, instead of writing here epsilon naught, okay, I'm just going to expand epsilon naught. Epsilon naught is, in fact, 1 divided by 4 pi times k. And so I can write it like this. And you don't always have to do that. Sometimes you can leave it as epsilon naught. But I want to show you how the 4 pi cancels here to give you a simpler formula. So the 4 pi will cancel here. The 4 pi will cancel there. And now I get 1 over r squared. That's a fraction times Q enclosed times k. And then I end up getting this right here. Now, some of you have asked me a question. They said, well, wait a minute, can I just really multiply these two fractions by each other? Let me just quickly give you an aside on that and say, imagine I had something like this, 1 over 5, and it was multiplied by 1 over 4. Is that really equal to 1 over 5 times 4? And the answer is yes. Those things are exactly equal. So I can take this fraction here and multiply it by this fraction here, and it is exactly the same thing as 1 times q enclosed over the product of these two things. So yes, that is actually a legal operation. So the upshot of this is that we get this formula for the electric field. Now notice something about the formula. K is a constant, okay? Q is something given in the problem. I'm giving you the amount of charge that's enclosed. And R is going to be some distance from the charge. I can be at this distance from the charge, or I could be very far out from the charge, or I could be, very close to the charge. So for any R that I pick, I can plug that into the formula and calculate the E at any distance. That's the beautiful thing about this formula, is I can plug in any type of R. And what you can notice from looking at the formula right away is that as R gets bigger and bigger, the E field will fall off. It'll get weaker and weaker, right? Because E is inversely proportional to R squared. So pretty quickly it'll drop off. So if you're far away from a charge, the field will be very weak, but as R gets smaller and smaller, the electric field will get stronger and stronger. So that's the idea behind this. So that's our formula. Now, can I apply it for some sort of concrete situation so you can see numbers being used? Let's try that, okay? So let's say we've got this situation. I've got a little point out here, and I want to know what the electric field is at some distance r from this charge, right, like that. I'm going to use this formula, okay? Now, I'm going to give you some values. How much charge do we have in there? What is the value of K, and how far away are we? That's the next slide here. Okay, so let's say we have these values. Let's say the charge is 1.5 microcoulombs. Say the distance is 1.2 meters. That's R. That's how far away we are. And then K is something we'll always give you, 9 times 10 to the 9th Newton meters squared per coulomb squared. So we plug these things in, and that's what we have in the next thing here. So I plug in these values. So this is just K times Q over R squared. And if we plug all those values in, we get 9,375 newtons per coulomb. That's the electric field 1.2 meters away from this charge in here. So just to sum up, we used Gauss's law to calculate the electric field around a point charge, and then we applied it for a given value of Q, a distance R, to calculate what the E field would be at that point. If I asked you at a different distance, then all you'd have to do is plug in a different value of R into this formula, and you could calculate E. I'm not saying I'm going to ask exactly this on the exam, but if I did, you'd know how to answer it now, wouldn't you? I hope this has been helpful.